Good afternoon, everyone. We will start soon. Once the participant count reach 100, we will start soon.
ఏవో చేయకూడదు చూసుకోవాలి. వీళ్ళు స్టార్ట్ అయిందా? స్టార్ట్ అవ్వలేదా? అమ్మ నాది.
Good afternoon, everyone. I hope we all had a refreshing lunch and we are ready to give you another insightful session of our today's lecture series. As we move into the afternoon session, it is time to explore one of the most essential aspects of research and industrial analysis, which is statistical quality control and data interpretation. So, in today's rapidly advancing scientific world, maintaining quality and making sense of data are the two pillars of research and reliability. Whether it is a food processing sector, engineering, or product development, statistical tools will guiding us in ensuring a precision, minimizing errors, and making the data driven decisions. So to enlighten us with on this topic, we have with us Ms. Abipriya, research scholar in the Department of Food Process Engineering, NIT Rourkela, to join with us. So the session is yours, ma'am. You can share the screen. Please give us 2 minutes. We will be sharing this screen soon.
Good afternoon, everyone. I am Avipriya Patra, a PhD scholar in Department of Food Process Engineering at NIT Rourkela. Today, I'll be presenting on statistical quality control and data interpretation in food process engineering. In simpler words, this presentation is about how we can use statistics to make sense of our experimental data to improve the product quality, analyze trends, and make our food processes more reliable and efficient. We'll go to the next slide. Here. Here is the why statistics in food process engineering. Let's understanding the statistical play in such an important role in food process engineering. When we produce food, whether it's a milk powder, bread, or chocolate, we want every batch to have the same texture, color, and safety. But many factors can affect quality like temperature, moisture, pH, or even the operator error. Statistics helps us control these variations like firstly ensures quality and safety by monitoring the parameters like pH, temperature and moistures we can ensure the product are consistent and safe. Secondly, by optimizing the processes, it helps to find the best combination of process parameter. For example, what ultrasound power, which type of ultrasound power gives the highest protein yield. The thirdly, it reduces the errors. Instead of relying on the guesswork, statistics give us the objective results that can be trusted. Ensures compliance will be the fourth objective, like the many quality systems like HACCP and ISO require the statistical records for audits and certification. So, in short, statistics in food engineering are like a compass that guides us towards consistent quality and statistical reliability. Let's go to the overview of the statistical quality control or SQC. Now, SQC means using statistical tools to monitor, control, and improve the product quality. It includes three major components: descriptive statistics, inferential statistics, and control charts. Descriptive statistics means it summarizes your data like mean, standard deviation, or range. For example, the average moisture content of the biscuit in a batch. Inferential statistics, this helps draw conclusion from a sample about the whole population, like testing if a new drying method is really increasing the yield. Control chart. These track process parameters over the time to identify when the process goes out of the control. Hence, in food engineering or food processing, this approach helps us to detect deviations early. For example, if the moisture in a cracker batch starts increasing beyond the control limit, we can correct it before the crackers becomes soggy. Then comes to the types of data in food process engineering. Before analyzing any data, we must understand the what kind of data we are dealing with. We generally handle two main types. One is qualitative, that is categorical, and another is quantitative, that is numerical. Qualitative data are descriptive, like the product type means cereals, dairy, or beverages, or any sensory scores like poor, fair, good, or excellent scores. We cannot perform arithmetic on these values. We only classify or rank them. While quantitative data are measurable, for example, protein yield, temperature, moisture content, or pH of juice. Quantitative data are further divided into two types. One is discrete data and continuous data. Discrete data will be the countable values like the number of defective packets in a batch. But while continuous data, it measures its they are measurable values that can be take any number like the temperature, the protein concentration, like this. Understanding this distinction helps in choosing the right statistical test later. Then we'll come to the types of statistics. Let's talk about two main branches of the statistics. One is descriptive statistics and another is inferential statistics. Descriptive statistics are used to summarize your data like mean, median, mode, variance, and standard deviations. Inferential statistics are used to make the predictions and draw conclusions about a larger population from the sample data. For example, if we measure the protein yield of 10 different samples and want to conclude something about the whole process, that is called as the inferential statistics. Let's come to the descriptive statistics. Descriptive statistics are methods used to summarize, organize, and describe the main feature of the database. They help us understand what the data look like without making in predictions and inferences. In simple words, descriptive statistics turn raw numbers into the meaningful summaries like the average, range, or the spread of your data. The purpose of descriptive statistics to simplify large data into a few understandable values, to describe the trends, patterns, and variations in the data, and to provide the snapshot of experimental results before the deeper analysis like ANOVA or regressions. There are different types of descriptive statistics. It measures the central tendency, firstly, like so the center or the average value of the data. Mean, that is the sum of values divided by the number of values. Examples, average protein yield from different protein plant variables. Medians, the median value when the data arranged in an order. Examples, the median moisture content among the 10 different apple species. Mode is the most frequently occurring value. Let's say the most commonly sensory scores in the test. Second way of a descriptive statistics is the measures the dispersion or the variability. So how the spread out the data are around the mean. It has three different types of variability like range, variance, and standard deviation. Range is the difference between the highest and the lowest values. Variance is the average of the squared difference from the mean, and the standard deviation are the square root of the variance, which shows how much values differ from the mean. For example, let's say the smaller standard deviations means all the samples have similar protein yield. However, the large standard deviation means the variety of yields which have significant difference within them. However, I won't go into the much details about the descriptive statistics since most of us have already learned in the basics earlier. In simpler terms, descriptive statistics just summarize the data we collect, showing us things like the average, the range, and the general pattern within the dataset. It helps us to get a quick snapshot whether our data look like before we move into the deeper analysis such as the hypothesis testing or the ANOVA. Before going for it, I'll just show how the Excel, it will, in the Excel, we can show the descriptive statistics. Like these are the three different apple varieties and these are the different moisture content we have taken from each varieties. And we can analyze from the Excel files the average, median, mode, standard deviation and variance. These are the average values of all the replicates of three varieties. Standard deviations, median, mode, variance can be calculated through Excels easily. Then we go for the Next slide. Inferential statistics. Now that we have seen the descriptive statistics, which only summarize that we have already have, let's move on to the inferential statistics, which helps us to go one step further. Inferential statistics allow us to draw conclusion or to make the predictions about a larger population based on the small sample of the data. For example, imagine you collected protein yield data from 10 different leaf samples. Instead of testing every leaf in the world, we can use the sample data to estimate the average protein yield for the entire populations. This is what the inferential statistics do. They use the probability to tell us how confident we can be in our results. There are two key parts here. One is the three key parts here, like the hypothesis testing, p-value, and confidence interval. In hypothesis testing, where we check whether an effect or any differences is real or just due to the chance. For example, we might test whether the ultrasound extraction really increase the protein yield. While the p-value means the probability value, it tells us the probability that our result happened not just by luck. A small p-value like the less than 0.05 means the result is statistically significant. In other words, it's not random. In general, or in basically in food process engineering or any other system process engineering, we generally took the p-value as less than 0.05 value. For more precision, we can take it as 0.02 or 0.01 as well. The confidence level or interval, it is noted as CI. This gives us a range of values where we expect the true result to fall. For example, we might say that we are 95% confident that the real protein yield within this range to this range, and where the probability or the p-value will be the less than or equal to 0.05. So in short, descriptive statistics describe your data, while the inferential statistics help you to make the decisions and the predictions about what those data mean in the real world. Let's come to the next slide. Here we are going for the introduction SPSS software. SPSS stands for Statistical Package for Social Sciences, but it's widely used in food research too. It has easy graphic interface, so we don't need to write code. It handles larger data sets very efficiently, performs key analysis like t-test, ANOVA, correlations, regression with just a few clicks. It also helps to create graphs and chart for the report. Thinking of SPSS as your digital lab partner, it takes care of the math while you focus on the interpreting the results. Here I will show the how SPSS softwares look like. It can be easily downloaded from any other from any type of softwares field, or you can download it as a crack version also if you are studying in an institution or any universities. They there you also can get the licensed thing. Here I have the SPSS software. It is IBM SPSS Statistic Data Editor 24 editions, and this is the looking like of the SPSS software. This is the variable tables. We can put the all our data sets, and these are the toolbar for the analysis of all these statistical parameters. Later we will see how we'll enter the data in it and analyzing the every species parameters. Let's go for the data entry and variable setup in SPSS. In SPSS, we firstly define the variable in variable view. Like you said, the name, type, or scale, like like in nominal or nominal or scale of the variables. Then you enter the reading in the data view, like the moisture content, yield, or any other score of the in food processing parameters. For example, we supposed the moisture content of a different apple species. So each variety will be the variable and each reading goes to the data entry. Since the data entered, the SPSS compute the averages, the plot graphs even run the ANOVA other statistical parameters. While so, from the how to put the data in the SPSS software. Likewise, this is the three types of variety of the apples, and this are the different moisture content value. So, moisture content value in SPSS, the will represent each variety using the numerical codes like 1, 2, 3 instead of writing the full name. Or so instead of writing apple A, apple B, apple C, we are writing represented as it 1, 2, and 3. And the apple variety number will be entered in one column of the variety like the independent variable, and the moisture content will be entered into another variable like the dependent variable. And if the varieties have a replicate number of data, like the apple A and apple B, apple C have the replicate of moisture content, so we will repeat the same variety code for the each variant. Like I'll show the okay. Here I'll write. We have in Excel, we have seen that the moisture content of each varieties have seven replicates of the moisture content. So we'll put for one variety as a one number, means one, 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 like up to 7 times. See, then we'll put the moisture content values. Copy and paste. Here, if we have more than one variety, the second variety will be represented as 2. If it is the replicate will be the 7 times, then we will put 7 times for the same variety. Okay. Then we'll go for the next batch, copy and paste. Hence, if you have more than 2 varieties, you can also write as 3, 4, 5 for the each variety or each batch or the each sample type, and the variables will be the presented as their respective replicates. These are the independent variable data sets and these are the variable data sets. Okay, let's go for the next PPT slide. Okay, let's come to the t-test. A t-test used when you want to compare the means of two groups. Example, suppose we extracted protein before and after the ultrasound treatment. So the null hypothesis or the hypothesis will be there will be no difference between two yields, but the alternative hypothesis will be that the ultrasound changes the yields significantly. So here, by the running t-test, SPSS gives us p-value or probability value. That is, if p is less than 0.05, then we reject the null hypothesis, means the ultrasound had significant effect on the protein yield. In simpler words, t-test shows whether the improvement we see is real or just by the chance. Okay, then let's comes to the different types of t-test. different types. There are three different types of t-test. Is one sample t-test, independent sample t-test, and another is paired sample t-test. One sample t-test is to test whether the mean of a single sample is significantly different from the known or hypothesized value, which is called as the test value. Let's suppose, let's go to the Excel file. Okay, this is the two types of cookies, which is without millet and another is with millet, and there are different types of moisture, different moisture content we have measured for the both type of cookie. Then we'll see that the cookie with this moisture content will run in the SPSS for the t-test value. Okay, copy and we'll put as the, let's delete first. Okay, put the variable. Okay, the one variety will be tested for the one sample t-test. So I'll put as 1. Okay, then we'll go for the t-test analysis. Select both the group, then go to the analyze tool, and then compare means. In compare means, you can see that one is descriptive statistic, that is means. It will show the means, median, standard deviations, variance in that. I'll not go for this. And there are three types of t-test. One sample t-test, independent sample t-test, paired sample t-test. And this is the one way ANOVA will go for the later. Here we have to test for the one sample t-test because we have put one variety at a time. Then we go for the one sample. Here our variable will be the column variation 2. That is will be the test variable. Okay. Okay, let's not suppose we just delete that first variable because we have only one data. So it's better to put in a variable 1. Just click as that. Compare means one sample t-test. So this will be the test variable. The test value means the hypothesized values. Let's suppose for the best betterment or for the best sensory score, the cookies have the moisture content having 42%. So options, let's go to options. This here the confidence interval level is from 95%. It means the probability value is less than equal to 0.05. Continue, then press OK. Here we'll see that one table is there. Here we can see the descriptive statistics, that is mean, standard deviation, and standard error mean. Here we'll see the one sample t-test, and here we'll see that the significance level, this is 0.208, which is not less than 0.05. Means the p-value here is not less than 0.05, which shows there is no significant difference between the mean value of all the cookies and the hypothesized and the test value. Let's suppose again we have to analyze the t-test. I'll show how it will be the significantly different. We'll go for this. Let's suppose the test value will be the 30%. Let's suppose our best sensory score, the cookie has to be the moisture content of 30%. We'll go for the same confidence level. Continue, then press OK. Here we can see that the significance or the p-value is less than 0.05, means it has significance difference between the mean value and the hypothesis or the test value. Okay, so here we can say that here it can predicted that the how much will be the test value or hypothesis value, and for the batch value. From this one sample t-test, it can be easily predicted from this significance level. Okay. No. Let's go to the another point, and is the independent sample t-test. The purpose of independent sample t-test is to test whether two independent groups or not related groups have the different means. Like we measure the moisture content for two different types of cookies, like cookie without millet and cookie with millet. There are different types of cookie. We have to see that whether they are significantly different in their moisture content or not. So we'll just copy the values of moisture content and put into the variable box. Okay. Here we have to put the one variety as 1 and second variety for the 2. Okay, let's go for the analyze. Compare means then independent sample t-test. The test value is the group the column 2 will put the test value in for that, and the column 1 will be the grouping variable. Define groups. The group 1 is the variety 1, and the group 2 will be the variety 2. And press continue. Options will be the same. The confidence interval percentage will be the 95%. Then click continue. Then click OK. We'll get independent sample t-test value. This is the descriptive statistics where we can find the mean, standard deviation, standard error mean. And this is the table of independent sample t-test. Here we can see that the significance is not less than 0.05. So which it can mean that there has no significance here we can see that the significance level is less than 0.05, which means that there has the means of two different different types of cookie had the significance difference in their moisture contents. Okay. Next, the third one is paired sample t-test. The paired sample t-test to test whether the two related or paired measurement differed significantly on the same subject measured before and after treatment, means before adding millet and after adding millet, how the moisture content will be differed significantly. It can be shown by the paired sample t-test. Let's we'll go for first we'll delete all this, clear all these things. Then first we go for the batch 1 without adding millet. That will be the variable 1, and the second variable will be the adding millet. Okay, this is the two variables. We'll see that after adding millet, how the effect of moisture, moisture content is differed significantly or not. Compare means, let's go to the paired sample t-test, and here the variable 1 will be the placed as a column 1, and the column 2 variable 2 will be the set as column 2. Okay. Then here we can see that here's paired sample t-test had significance level of less than 0.05. It means that there has been a significance difference between the moisture content when adding the millets. Let's suppose it has no difference. Means suppose in Excel file, there are two different types of moisture content, two batches of moisture content. We'll check whether the pair t-test clarify that there has been a significant difference in their moisture content or not. Just copy and paste. Okay. We'll go for the analysis, compare means, paired sample t-test. The same variable 1 will be put on the column 1 and variable 2 will be put on the column 2. Click OK. Here you see the significance or the p-value is greater than 0.05. It means there has no significant difference between the means of moisture content of different types of cookie. So it clarifies whether the addition of anything to any process or any technique or any materials to the sample, whether it is significantly differ or not to the whole batch. Okay, let's go to the another slide. Okay, let's come to the introduction to the ANOVA. ANOVA is the analysis of variance. When basically the t-test is for the two types of batches or two types of sample. Basically, it is for the two groups. But when the groups are two or more, we'll apply ANOVA for the statistical comparison. So running the multiple tests, hence when we have 3 or more groups, t-test is not enough. So running multiple t-tests increases the chances of error. Hence the ANOVA comes, that is analysis of variance, compare the all groups all together. For example, comparing the protein yield as 3, 30, 60 and 90% of ultrasound amplitude. There are three different groups, was 30%, 60% and 90%. So it cannot be statistically compared with the t-test value. So ANOVA splits into total variations into between the groups due to the treatments and within the groups due to the random error. If the variation between the groups is much larger, it means the treatments truly differ. However, the ANOVA only tells us at least the one group differ, not which one. That's why we use post hoc test and we'll talk it about the later. Let's come to the one-way ANOVA, how it is functionalized. And one-way ANOVA is used when we have one independent variable and another is the dependent variable. Like there are three different heat treatments, and the dependent variable will be the enzymatic activity. So one-way ANOVA tells us whether the enzymatic activity significantly changes with a different heat treatment or not. We'll see by the example. Here are the different temperatures and this is the residual enzymatic activity. And we'll see that whether the one-way ANOVA shows there is a significant difference or not. So first we'll clear the variable columns. Then we'll put these three types of temperature. So we'll take as 3 test variables like 1, 2, 3. And there are 3 replicates. So we'll put as 1 as 3 times, 2 3 times, and 3 times. Okay, we'll get the the independent variable, and the dependent variable is residual enzymatic activity. We will put in the next column for the variable for the dependent variable. Select both, go to analysis, compare means, then we'll go for the one-way ANOVA. Here, dependent list will be the variable column 2, and the factor is column 1, that is temperature. Well, okay, here no post hoc will be applied because I'll showing how one way ANOVA differs the significance level between 3 different temperatures. Okay, we'll just go for the descriptive statistics. Okay, then click OK. Here you can see that this is the descriptive statistics, and this is the one-way ANOVA table. Here you can see that the significance level is less than 0.05. It means the between the groups means between the temperature levels, the residual enzymatic activity had significance different level. So we are cleared as of now. Then we go for the next slide, that is the post-hoc text. To ANOVA, we do post-hoc test to find which groups differ. Means we have seen that within the temperature profiles like 100 degree, 120 degree and 140 degree, there is a significant difference in the residual enzyme activity. But which temperature had significant difference, we didn't see from the one-way ANOVA. Here comes post-hoc test. This test makes the pairwise comparison while the controlling error. There are two types of post-hoc test. One is Tuckey's test and another is the Duncan test. First, we'll see the both types of post-hoc test. Then I'll compare with by help of the SPS of software. Let's understand this comparison in the simpler terms. Duncan test, it is more sensitive and detects even smaller difference. It is useful for the exploratory works when you don't want to miss any subtle effects. But in Tuckey's test, it is more strictly and confirms only the strong and reliable differences between the groups. For example, the protein yield at 30, 60 and 90% of ultrasound amplitude. Duncan may show all the 3 amplitudes having significant different protein yield values, but in Tuckey's may show only 30 and 90% of the amplitude differ significantly. So analogy of the two tests will be like this. The Duncan test is more like the metal detector, while it beeps even if at tiny signals. But in Tuckey's test, it is like a filter. It only passes strong and clear signal. Basically, in research, Duncan uses for the early exploration, but while the Tuckey's is for the more confirmatory publication level work. Then we'll see in the SPSS software how it is differ from there. Okay, here has three different ultrasound amplitudes, and this is the different protein yield at each amplitudes. We'll see in both tests, okay, and Duncan post-hoc test and Tuckey's whether it is different or not. Okay, first we'll clear the columns. Let's comes to, there are 4 replicate measurements of protein yield at each amplitude. So we'll go for the 4 times of 1 and 2, then 3 for 90 degree, 90% of ultrasound amplitude. Then we'll just copy and paste the value of the variable data set as the dependent variable. Okay, we'll see for the one-way ANOVA data. compare means analyze, compare means one way ANOVA. Okay, dependent list will be the column 2 and factor is the column 1. Here we will go for the postdoc. Postdoc will be the first we will say as a Duncan test. Significance label is 0.05. Okay, options descriptive, continue, then click OK. Here, this is the descriptive, this is the ANOVA. ANOVA is showing that significance level is less than 0.05, means there has a huge significance difference between the groups. But in post-hoc test, like we have tested as for the actually taken Duncan test, here we can see that here we can see that 1 means 30% of amplitude is more significantly differ than the rest of the amplitude, like 60% and 3%. Here you can see that in a table that it is showing as 1 and 2. Here it is showing the values of significance labels of each terms, like the 1 it is represents the lowest significance level, and 2 it represents the highest significance. If it is more than 2 or 3, the significance levels will be differed much more than the test sample. Okay, so here one means we'll put represented as A, means slightly significantly differ, but two columns represented as B means not slightly or more significantly differ than the first table. So we will put in the Excel file that here the 30%, the table is for the 1, means the significance level is slightly significant difference, but the rest of the 60 and 90% of amplitude, it is showed that it showed higher significance level, significantly differ. So we'll put as B here. So from this notation, we can predict that the 30% has less significantly differ at 30 amplitude, a significant difference of the protein yield, while in 60 and 90%, the protein yields are not are higher significantly differ from the 30% amplitude. But while running with the Tucky's test, we'll see the different significance level. Let's say first we'll just go for the analysis and compare means, go to one way ANOVA, same thing, but in post-hoc we'll click on the Tucky's, not in Duncan, continue, okay. This is the descriptive. Significance level is same. One way ANOVA shows that there has a significant difference between the groups. While in post-hoc test, we have taken the Tucky's. Here we have taken, we have seen that in 1, 2, 3 variable variety or 30%, 60%, 90% amplitude, there has different significance levels. Means one source, as I previously said, that A means slightly significant differ. 2 table means B means more significantly differ from the column 1. Got it? So I'll represent it as like 1. In one column, we have seen that 30% had the slightly significant difference. Let's put the value, let's put the notation as like in Excel for the Tucky's. Here we'll put as A. Okay. But in B means 60% amplitude, there is the significance label at the 2 column, means it represents between the A and B. So the notation will be A, B. Okay, got it? Next we'll go for at three variety means the 30% amplitude. It is showing that at the significance level at column 2 means only column 2 means its notation will be B. So here you can see that in Tucky's test, the 90% had more significantly differed protein yield as compared to the 30% ultrasound amplitude. But while at 60, but not with the 60% amplitude. But in Duncan test, both 60% and 90% amplitude gave significantly differed protein yield as compared to 30%. So here we can see that Tucky's test is more reliable and more comfortable for the comparison between the significance levels. Okay, we'll go for the next slide. Here will come as the two-way ANOVA test. When the in previous slides, we'll go for the one-way ANOVA means we put one factor at a time. Means independent variable is one. Dependent variable we are not talking about, but the independent variables like the variety of the samples or the temperature of the for the residual enzymatic activity or the ultrasound amplitude levels for the protein yield. These are the one factors. These are considered as a one factor. So for the one-way ANOVA, we are considering one factor at a time. But when we are considering two factors altogether, then like the ultrasound amplitude and the extraction time, then we will use two-way ANOVA. It tells us the individual effects of each factor. The interaction and the interaction effect means both the factors, how it is affected the dependent variable, like say the protein yield means their interaction effect, how it is affected significantly or positively significantly or negative significantly on the protein yield. Let's go for the analyzing in the SPSS software. This is the two-way ANOVAs. This is the table of a moisture content of a three different sample type A, B, C, and there are for the samples are stored for the moisture content analysis for 3 days. Means the moisture content has been recorded as 3 different days as a triplicate. We'll see that how the two factors here, the two factors are, one is sample type and another is days, number of days. How the different two factors affected the moisture content significantly or non-significantly. Okay. Okay. For this, I have already represented the sound for the SPSS software. Like I have noted the day as 1, 2, 3 and the sample as A, B, C and the values of moisture content like this. Okay. Then we'll just put first variable at a time, first independent variable. Just cancel it. First, I'll clear the all values. First, this is the factor 1, means number of days. Then we'll go for the sample type. As we cannot show or we cannot present any other than numericals like A, B, C or I, second I, third I, or any categorical names on the SPSS. So I have to put the sample types as 1, 1 and 1.2 and 1.3. So for each day, I have taken three replicates for each sample type. So I have to put like this 111, then 1.2 for the sample 2. Then for the sample 3, 1.3, 1.3, 1.3. Likewise, I have to repeat for the same day 2 and day 3. Okay. Then we'll take the dependent variable, that is moisture content, and in the column 3. Okay. Here we can easily see here, this is the column 1, that is represented the variable 1, like number of days. And this is the column 2, that is the independent variable 2 or factor 2, that is the sample type. And this is the variable dependent variable column where we are seeing the moisture content at each sample type and each days. We'll go for the two-way ANOVA. We'll go for the compare means. Okay. Compare means. No. Compare means. This is not the mean value. Here we don't find that. We'll go for the general linear model. And in the general linear model, as we have one type of dependent variable, so we'll go for the univariate. Here, the dependent variable is on the dependent table. Fixed factors are two fixed factor. This is the two fixed factor. And where we'll go for the full factorial model, plots will be this is there are two types of plots. One is factor 1 and another is the factor 2, means independent variable 2. So I'll go day 1 for the horizontal axis days, and number of and the sample types will be the separate lines. Click add, continue. Then we'll go for the post-up test for both the factors. Like I have said, Takis is most reliable and mostly used in the food process engineering processes. So we'll go for the Takis. Then we'll go for the options. Like we have chosen three types of linear formats. Okay. And the displays will be the descriptive statistics. Let's click continue. Then click OK. It will take some time. Okay, it will get. We have seen that this is the descriptive statistics I have already discussed. Here we'll see that the between the two factors, here we can see the significance labels, like variable 1, variable 2, there is no significance level. P value is less than 0. So it means we'll see that there has been significant difference between two groups. While in seen in the Takis test, this is the important one. While in C, there is the for the variable 1, this is the post-up test. For the variable 1 means number of days. means say day 3, day 2, day 1. This is the like this. And the column will represent the how much the significant label differ from the one another. Like day 3 is slightly significantly differ, while day 2 has large significantly differ, while the day 1 has the largest significantly differ from the data set. So we'll put like the same, and I'll represent for the variable 1 as the small ab, like we'll put first the values like as a day 3. Sorry, as day 3 as the slightest significant label, so I noted is a small a. And day 2, while you here see that the day 2 has the slightest higher significance label, so I'll put as the b, and day 1 as the small c. Okay, let's this is the for the factor 1, that is day number of days. Number of days means according to the days, how the moisture content will be significantly different from each other. Then while go for the variable 2, this is the variable 2 post-hoc test. Here you can see that the variable means 1.1 is the sample 1, 1.2 for the sample 2, and 1.3 is the sample 3. Here you can see, as I likely said, that key 1.1 means sample 1, sample A has the least significant label differed from the other, while the 1.1 means sample B has a slightly higher significantly differ from the other two. But in case of sample C, that is the highest significantly different from the other data. So I'll put like this only, means smallest significant label will be presented as A, then B, then C. As I have already put small abc for the variable 1, like number of days, so I'll put for the capital ABC for the sample type. So as we have seen that sample A has a slightest significance label, so we'll choose as the we'll choose as here I have already put, we have choose as the sample A as capital A, for B as capital C, capital B, and for sample C as the capital C. Okay, got it? For like as the for day 2, here we have significance label as the small c for the slightest significance label, but in case of the sample type A, it has a significance label of A, capital A, means the smallest significance label as while we're comparing with the sample type. So here A, B, and then put as the C. Okay. Same as for the day 3, means small a will represent the slightest significant label as compared to while comparing within the days, and capital A will signifies the significant difference within the sample type. And same procedure will be samely go for the other sample, other moisture content. Okay. Let's go to the next slide. Okay. This is the predicting and optimizing the response using the regression. Means we have seen that SPSS that more than one factor we have compared with statistically by two-way ANOVA test. but with one variable. If suppose we have multiple variables, means multiple variables, like instead of protein yield, if we will choose that protein extraction yield, recovery yield, efficiency, all these will be the dependent variable. So we need as a regression equation for the satisfying the interaction between two or three independent variables which affecting the multiple dependent variables. Okay. So after identifying the important factor using ANOVA, we build a regression model. Okay. Regression gives us a mathematical equation. Here you can see that this is the format of a mathematical representation of regression equation. Here we can see that y equal to beta naught plus summation of beta I plus xi into xi plus this is the whole terms. Y represents the dependent variables, while this is the intercept. This represents the intercept, and these are the coefficient of each independent terms. Like this is xi represent the independent variables, and xi square will represent the quadratic terms of the independent variables, while these terms represent the interaction between the two independent variables. So we can use this equation to predict the yield under any conditions and find the best combination of the maximum output. So ANOVA tells us what significance regression quantifies, what significance, while the regression quantifies the effect, and the response surface visualization shows the where the optimum results will be lie. There are three types of statistical representation for multivariate processes, like if we have two or more factors or independent variables, or two or more dependent variable. So we have three types of statistical analysis: ANOVA, significance levels; regression tells the quantify the effect; and the response surface that visualize the interaction and optimize the value of that particular dependent variables. Let's goes to the design of experiment. It is basically a structured way of planning experiments instead of changing one factor at a time, as we change the several factors together in a systematic and scientific manner. The goal is to understand how different factors affect our outcome and to find the best combination for the desired results. For example, in my case, the independent variables might be ultrasound amplitude, extraction time, solvent to solute ratios. But the dependent variable can be the protein yield, efficiency, protein recovery, and the protein content. Rather than testing this randomly, design of experiments helps me to plan the experiment in a such a way that I can get the maximum information with the minimum trials. It is like the following when design recipe: instead of randomly mixing ingredients, as he used planned approach to see how each ingredient changes the particular yield, efficiency, and the content of the sample. Once we collect the data using this systematic plan, we can also use statistical tool to analyze how each factor influences the responses and whether any interaction existed between them. Now, the common type of a design of experiment is the factorial design, where we test all possible combination of factors. That helps us understand not only the individual effect, but also how two or more factors interact. As we have already said that in two-way ANOVA, I clicked on the full factorial design. Means it will show that not only the individual effect, but how the interactions between two effect, means the number of interaction between the number of days and the sample type will affect the moisture content significantly or not. Okay, later we can or not. So hence later we can move to the response surface methodology, as we use even more advanced design like box Benker design or central composite design to build the 3D surface models. These models helps us to and predict and optimize the responses, like the finding the perfect conditions for ultrasound amplitude, time, and optimize the solvent to solute ratio to maximize the protein yield. So for this design of experiment, we'll go for the design expert software. It is another statistical software which we have seen that we will see or check the how the multiple factors or independent variables affect the dependent variable significantly or not. Let's comes to the comparison between three basic design which has commonly used in food processing sectors. The factorial design, like a testing every possible combination of your factors to see how the individually and jointly affect the results. Okay, let's say we want to study the effect of ultrasound amplitude and extraction time. So here will be the 2x2 factorial design at the 4 possible experiment. Like here it can be shown like that. Here, the power time will be combined as lower short, lower long, higher short or higher long. Okay, there are 4 different types of combination we have to study for the maximization of the protein yield. Okay, it is for in the simpler words, it's like a testing all the recipes to see which combination of the ingredients gives the best value. The advantages will be the easy to set up, helps to understand the main effects and interaction, while it has the biggest limitations, like it will become huge when the many factors and many labels of the dependent variable will be used. Hence, it will come as a box banker design. The box banker design is like a smart shortcut, as it tests the combination that give you enough information without needing to test every corner of the design space. The simpler example will be if you have 3 factors, like I have said, ultrasound amplitude, time, and solvent ratio. The design will test them at which combination, what on combinations at within the middle or the edge of the combination, not in the extreme corners. It is like testing at the balance point, not too high or too low of the combinations to build the curved or quadratic model. In simpler words, it's a testing it is by slightly changing the ingredients one at a time rather than trying every extreme combinations. The advantages are huge in the box bunker design, like the fewer experimental runs than as compared to factorial and other central composite design. It is efficient for while we are using 3 or more independent variables, and the limitations is it is not suitable if you are concerning about the extreme condition. The third one is the central composite design, as we commonly call as the RCCD or CCD. It is a factorial design by adding the extra points called the central or axial points. These are the axial points. Okay. To better the capture the curvature in the response. In simpler example, if you start with the factorial combinations like high and low ultrasound amplitude and time, then add some center points that the average conditions are repeated for the precision. And the axial points will be the beyond high and low levels which detect the curvature. In simpler words, it is like the zooming out of a recipe experiment to also test a little less or more of each ingredients. The advantages is it is very accurate for building 3D response surfaces, helps to find the true optimal points. The limitations will be the needing more runs as compared to the box Venkat design. Sometimes it will include very extremely means high or low conditions. As we'll see, these three types of statistical analysis will be easily understood from the another statistical software, that is Design Expert software. I'll go and so we'll see it now. I have told you that these three types of designs of experiment can be done by the another software. It is called the Design Expert software. The Design Expert is a powerful statistical software which is used for the design of experiments and response surface methodology. It helps in planning, analyzing, and optimizing the experiments efficiently. The software can generate different designs such as the factorial, box Venken, central composite, and others. It provides 3D response surface plots and contour graphs which to visualize the factor interaction and locate the optimum condition. Why it is widely used in the chemical, pharmaceutical, food process engineering research for the process improvement and optimization. It makes a complex statistical analysis essay, which is visual interpretation friendly and even for the non statistician. Okay, we'll first go for the check to see the how it will works. So for this, I have taken three independent variables like extraction time, ultrasound amplitude, and solvent to solute ratios at two different levels, means low and high, and the center point will be represented. Means for the extraction time, the low value has been considered as 5 minutes and the high extraction time as considered as the 20 minutes. But while in ultrasound amplitude, it is 30 and for high is 60. In case of solvent to solute, the low and high points are 20 and 50 respectively. These are the center points which can be calculated by the sum of the low and high values divided by 2. It can be calculated by this, and there are three different variables like phenolic compounds, flavonoid, antioxidant activities of different treated samples using the ultrasound assistance. So we'll see at we are seeing that there are three different independent variables and three dependent variables. Three independent variables will be combined in such a way that the dependent variables will give the maximum output in this whole entire process. So this is the main theme of doing the design export. So it will how it will be gone that this is the design export software. Okay, I'll just show you how to run like this. Means this is the design export software, and we have to click the new design. At the new design, there are different design of experiment we can statistically represent. From this, we are mainly considered or basically considered factorial design, response surface designs. And in response surface, there are different types of statistical parameters like central composite design, box Vencan, optical or custom design, etc. From these, we are basically used box Vencan and central composite design. We have discussed the comparison between them. So if we are taking the box Vencan design for the three independent variables, there will be the total runs of 17 runs. But in case of factorial, there will be the more runs in between three independent variables. So this is the big limitation for the factorial design. To eradicate this, box Vencan design is the best method to optimize and to design the whole experiment. While in central composite design, that will be the 9 runs, and 9 runs is that because the central composite design consider very extreme conditions of three independent variables. So, for example, I am just giving you the how the box Vencan design we follow. Like there are 3 columns. If you have will have more than 3 independent variables, we can increase the numerical factors, so it can be the independent variable we can put. Okay, so we have 3 independent variables. So one is time, unit is minute, low value is 5, and the higher value is 20. Okay, then the second independent variable is the amplitude, ultrasound amplitude, that is expressed by the percentage, and the less will be, let's see, 30, and the high will be 60, 30 to 60. So these are the extreme points, or these are the point within this range. The maximum of all the dependent variables has to be count. So this is the third independent variable, which is solvent to solute ratio. That is expressed by the ml per gram. And let's see the minimum and highest value, 20 to 50. 20 to 50. Okay, we have put, after putting the lowest and highest value of the all these independent parameters, then we'll go for the next. This is the how many responses. Responses we'll call as the dependent variables. The dependent, how many are the dependent variables will be. We have 3 or 4 dependent variables, so we'll increase the numbers by clicking the up value. So how many it will be? Let's suppose 3 independent variables like total phenolic content, total flavonoid content, antioxidant activity, and the unit as well, like a gallic acid per gram, gallic acid equivalent per gram, quercetin equivalent per gram, then antioxidant activity is represented as the percentage. Then we'll go for the finish. Let's have a look on the table. This tables has the 17 types of different combination of independent variables, the time, amplitude, and solvent. And these are the 3 types different responses value. So this is the design of experiments which you will get from the design expert software. After getting this, you just have to run the experiment, run the ultrasound assisted extraction of any sample by this 17 runs, as well as taking as let's suppose the first run is 12-minute time, amplitude is 30%, and solvent to solute is 50 ml per gram. So we have to take the first run as the 12.5 minute, and taking and run the ultrasound at 30% amplitude, while the sample has to add it as 50 ml of solvent. Like this, the whole 17 run will be experimented as for the combination which has been shown here. So after that, in each combination, we'll get the value of phenolic content, flavonoid content, and antioxidant values. These are called as the experimental values. So these values will be put at the respective runs or the respective combination of factors. Here we'll put the experimental value. I have already done the experiment, so there will be no need to put again. I'll show you just the graph. This is the whole graph. Here you can see that at every run at each combination, there will be a particular value of phenolic content, flavonoid content, and active antioxidant activity. Okay. Then after that, what we'll do, I'll show you. So first we'll go for the analysis. In analysis, first we'll analyze in each dependent variable for their statistical parameters. So this is the TPSC. First we'll go for the phenolic compound. Then we'll go for the fit summary. It will show that the quadratic will be suggested. Means it will show that the quadratic regression equation which I have discussed with the linear quadratic terms and interaction terms will be presented in a uh, mathematical equation form. That has been suggested that in the column it has suggested that quadratic regression equation can is best fit for the phenolic compound. So we'll go for then next we'll go for the model. Model is the quadratic, and then we'll go for the ANOVA. This is the statistical ANOVA table from which we'll get that significance of each term of the regression equation and model. Here we can see that model, if the p-value is very less than than the 0.05. From this, we can see that if it is very less than, then it represented the model as significant. And there are the different coefficients of the regression equation. Like these three represent the linear coefficient. These three will be the interactive coefficient, and these are the quantitative coefficient. For this, we'll also get that the p value. How this each terms will affect the phenolic component. Like here 0.01, 0.001 means these two are significantly affecting the to the phenolic compound. Means the respective p values of the respective terms are time and the solvent to solute ratio. Means rather than amplitude, the extraction time and solvent to solute ratio has more significantly effect on the phenolic compound. While checking the interactive terms, we'll see that the more interaction between time and solvents is highly affecting to the phenolic compounds. Okay, let's comes to the residual factor. That is the one is lack of fit. Here we can see that if the lack of fit is it has to be non-significant, otherwise the model cannot be significant. Lack of fit means the error present in the model. The error present in the model has to be non-significant. While seeing from the statistics, this is the fit statistics, means how the predicted model is bestly fitted for the experimental values of phenolic content. The R square adjusted and predicted will be very closely difference from each other, so that the best fit will be happened. So from that we can also check this is the table where we can check the each coefficient each numbers or each numericals for the each terms present in the regression equation. Like this I can show you this is the regression equation format. Means TPC will be represented by the coefficient plus plus linear forms, and then the interaction forms, then the quadratic forms. Okay, so here the 26.86 will be represented at the beta 0, as I have shown you in the regression equation model. Okay, beta naught is the intercept without any independent variable. B1 is the independent variable coefficient, and this one is the B double I is represent the quadratic coefficient, and Bij represents the interactive coefficient. So as well as we have to put the each numericals with the respective coefficient places. So 26.86 is to be placed here. Then 0.21 will be placed as the linear terms of A. A means x1, means time. So it's the adjacent to this. Then similarly, all these coefficient will be placed adjacent to their respective linear or interactive or quadratic variables. Okay, here also we can see that some of the terms are positive and some of the terms are negative. That means this the positive and means if A, as we have seen, I will show you in the bigger figure. Okay. Okay, here you can see that A has the significantly affected the protein phenolic compound, and here the coefficient is plus, means plus 2.1, means it means the time or extraction time is significantly positively affected the phenolic compound. But while in case of others, means say the amplitude, let's say amplitude is a negative coefficient, it means it negatively affected the phenolic compound. Okay, and as well as it is seen is the solvent to solute ratio, it has the positive component coefficient, it means the positively affected the phenolic compound. Also it can be also seen from the model graphs. The model graph, this is the contour type graph. Another graph is the 3D surface graph. Okay, the 3D surface graph, we can see that that time as the in ANOVA, it can be shown AB, AC, and BC. The AC and BC has highly significantly affected phenolic compound. So we'll basically check these two coefficient. So here you can see that the in that model graph, as the time passes or time increases, the TPC has not much affected to the much affected. But while the solvent to solute ratio increases, it has been affected higher. Okay, in BC also we can check that the amplitude has no effect, but while solvent to solute ratio has been increased, the TPC has been increased to the maximum value. Similarly, we can see for the TPC. TPC, the quadratic equation will be suggested. Then we'll go for the model. Model, it has to be quadratic. It has said that the model is significant. Time, amplitude, and solvent are significantly affected the flavonoid compound. Lack of fit is non-significant. It has to be non-significant because error present in the model fit is it has to be it very less significant as compared to the model. But in a TPC, in a phenolic compound, we have seen that the lack of fit is significant. So we have to recheck or the re-examine the phenolic compounds in every runs, so that the error presenting the model, it has to be non-significant. Okay. gallic acid, uh, phenolic compound. And here the coefficient much affected, but while time, amplitude, and solvent are significantly affected the flavonoid compound. Lack of fit is non-significant. It has to be non-significant because error present in the model fit is has to be uh, it very less significant as compared to the model. But in a TPC, in a phenolic compound, we have seen that the lack of fit is significant. So we have to recheck or the re-examine the phenolic compounds in every runs so that the error presenting the model, it has to be non-significant. Okay. Error present error present Um, Hello, good afternoon. There has been some problem with the video, so I'll explain it in live. That we have seen that similarly in TPC, that how the significance of the model has to be examined and the lack of it of error has been examined. Likewise, for the fit statistics like R square, adjusted R square, all these things. Same will go for the all these variables which we will take, and the model fit has been will be examined for the fit statistics and the coded forms and their significance labels. Lastly, we'll just sum up with the model graphs. This is the 3D model graphs we have seen in the TPC phenolic compound, and from that we'll check how the uh, interactive term has been affecting significantly or non-significantly to the each response. Then we'll go for the optimization. Optimization is the form that at which point all the responses or the variables we have taken for the particular experiment will be maximized as per the requirement. So the time independent variable will be keep as per the concern. Like if you target any value that 18, suppose 18.5 minute is the target value, at this value we need the TPC or the other variables to be maximized, then it can be done. But I'll just show you putting into the in range. The amplitude, it will also be in range, and the solvent to solid ratio in the range. Then all these dependent variables will be maximized or minimized as per the constant experiment. So we'll take as for the all these values as the maximized value, for the where is this happening is the minimized value. Or after keeping all this maximized and minimized, we'll go for the solution, where we can see that at a specific time, amplitude and solvent ratio, the all these values are maximized, which we have kept as maximization, and all and the which we have kept the minimized, and it has the minimized value. So for this specific experiment at 20 minutes of extraction time with the ultrasound amplitude of 30% and this addition of solvent to solute ratio at 49.06 ml, we got phenolic compounds, flavonoid antioxidant for the maximized result, where the saponin which we have kept minimized value, it is stored the minimized. For these solutions we need another important term is the desirability. The desirability of the every model should be greater than 0.8. So if it is higher than the 0.8, the model is the best fit for the experiment, as we have the experimented. So here for the specific results, it has shown is a 0.86 desirability. So it shows that this specific statistical operation as the best fit for the experimental runs during the ultrasound assisted extraction. So this is all about the statistical analysis which we have performed in various food process operations, like from starting from to the descriptive analysis, ANOVA, then post-hoc test, and to the regression analysis. All these things we have covered briefly, and if you have any doubts, please ask or write in the chat box. I'll clarify as for my best. Thank you.
Now the session is open for question and answer. So if you have any doubts regarding the ma'am has taken, you can inquire through the WhatsApp or in the question and answer chat box also. Interactive session is much more recommended for this type of lecture. So if any doubts, please ask. You can also inquire in the WhatsApp. I guess there is no doubts, ma'am. We can end the session.
Thank you, Divya. Thank you, all the participants.
Thank you, ma'am. Thank you.